So the common ion effect can be defined in this fairly lengthy statement that says less of a slightly soluble compound will be able to dissolve in a solution that already contains the solution's ions. So what that means, if I take some of this out of here, if I had a container and this was just water and I wanted to dissolve, let's just say, AB into here, and let's say AB is only slightly soluble, then most of this AB would sit down at the bottom, but a few of these A and B particles would be able to dissolve because it's slightly soluble. However, if I were to try to dissolve the same amount of AB into a solution that already contains either A or B or both or whatever, if there's already AB present here, then even more of this AB will sit as a solid down at the bottom. The presence of those ions make that ionic compound less soluble. So let's consider what this might look like in the grand scheme of things. Here we have some zinc hydroxide, so it's not got any of our soluble ions in it, so I know it's going to be mostly insoluble. It's going to establish an equilibrium here and produce just a handful of zinc 2+ ions and some hydroxide ions. We know this KSP is going to be small because this is mostly insoluble. It's going to be very reactant favored here, and sure enough, we have a KSP of 3.0 times 10 to the negative 17th, so a tiny, tiny, tiny equilibrium constant here, and again, that favors the reactants over the products. But the question is, find the molar solubility of zinc 2+ in water. And just as a reminder, this term molar solubility just means the maximum that will dissolve. So max that will dissolve. And we're looking for the maximum amount of zinc 2+ that's going to dissolve. Well, let's write our equilibrium expression for this. We know that KSP equals the concentration of the zinc 2+ times the concentration of the hydroxide squared. Don't forget the squared because it's coefficient of 2. And now if we think about this, we know the value of the KSP that was provided here. The value of KSP is 3.0 times 10 to the negative 17th. So I'll go ahead and plug that in for KSP. 3.0 times 10 to the negative 17th equals. Now I'm looking for the concentration of the zinc here because when this equilibrium is established, that will be the maximum amount of zinc that water can hold. So I'm going to designate that zinc concentration to be X. But we have to think about the ramifications of that. If the zinc concentration is X, then the concentration of the hydroxide has to be 2X because this coefficient of 2 out front indicates that there will be twice as much hydroxide present at equilibrium as there is zinc. So we'll call the hydroxide concentration 2X, and don't forget your squared. As we go through and clean this up a little bit, that's 3.0 times 10 to the negative 17th equals, now whenever you go to distribute this power through, this is really 2 squared and x squared. So this piece right here is 4x squared. That 4x squared is being multiplied by this x. Let me clean this back up though. So you have 4x squared times x squared. This becomes 4x cubed. Now we'll divide both sides by 4. And whatever value that is, we will take the cube root of it in order to get rid of this power of 3 here. And when we plug it into our calculator, we find that x, which we have defined as the concentration of zinc at equilibrium, is equal to 1.96 times 10 to the negative 6th molar. So we can pause for a moment and think about what this means. This is the concentration of zinc at equilibrium. That is then the maximum amount of the zinc that's going to dissolve in this water. So that value, this 1.96 times 10 to the negative 6 molar, is the molar solubility. But we could take that a step further just for thinking purposes, and that means that 1.96 times 10 to the negative 6 moles of zinc 2 plus will dissolve in 1 liter of water. And that, of course, comes from these units right here of molar. Molarity is moles per liter. So this is just another way of saying that if you had 1 liter of water, it could support the dissolving of 1.96 times 10 to the negative 6 moles of zinc. And again, it's not very much zinc dissolving, but we didn't expect it to be very much. We have a very small KSP, and we knew this equilibrium was going to be very reactant favored, so very little of this product was going to form. Very little zinc was going to dissolve. But what if I wanted to find the molar solubility of zinc 2 plus in a 1.1 molar solution of sodium hydroxide? So we're not dissolving it just in water anymore, we're dissolving it in sodium hydroxide. But it's important to think about what this sodium hydroxide is going to look like. This sodium hydroxide, when it's dissolved, since it does have sodium, which is one of our soluble ions, this is going to completely dissociate into sodium ions and into hydroxide ions. Now, you're going to find over time and experience that these soluble ions tend to be irrelevant here. I'm more hung up on this hydroxide concentration here. So if 0.1 molar, let me try that again, 0.1 molar of NaOH goes in, then 0.1 molar of hydroxide is going to be present whenever you dissolve this sodium hydroxide. So what that lets us do is we can kind of just rethink this. I don't even care about this sodium. I just care that it's producing a 0.1 molar OH solution. Now, you might be asking, why does that even matter? Well, if you go back to our dissociation equation, we were trying to find, we're not trying to find, we were dissolving zinc hydroxide, and that was forming some zinc 2 plus ions, and again, 2 hydroxide ions. The problem that arises here is there's already 0.10 molar OH present in this solution before you ever even try to dissolve it. So if you think back to Le Chatelier's principle and what the implications of that are, you have a bunch of this product already present. That's going to cause this equilibrium to favor the reverse direction, which in this case, I forgot to write my little solid symbol, but in this case, that's the solid. The presence of this OH already here is favoring the formation of the solid, meaning less of this will dissolve, meaning we would expect to see a molar solubility that is less than if this was just pure water. So just as a reminder, when this was pure water, our molar solubility was 1.96 times 10 to the negative 6th. Now I would expect this molar solubility to be quite a bit less. But how can we prove that mathematically? And I'm not going to recommend that you use an ice chart every time, but I'm going to use an ice chart at least for this one moment to help visualize the problem that we're about to experience here. So initial, change, equilibrium. If we think about how much zinc hydroxide is there, nowhere in the problem is that provided. It's also irrelevant because it's a solid. It's not going to impact the equilibrium as long as there's some present. So I'm just going to call that sum. And we've already established this as a mostly insoluble ion, so our change is going to be basically 0. There's basically no change here, so at equilibrium, there's still going to be the same amount present. There's some present. It's irrelevant. So little of it dissolved that the concentration effectively didn't change. But if you think about the zinc, initially there was none of it present. We don't know exactly how much we're gaining, but we know we're gaining some. So 0 plus that x is going to be our concentration of zinc 2 plus at equilibrium. We can't ignore this change because we started with none, and now we have some, and that's a significant event. But if we think to the hydroxide here, we're dissolving this in something that's already got 0.1 molar hydroxide. So 0.1 molar is my initial concentration of the hydroxide. if you think about the change, technically it is going to be 2x. The change will be double whatever the zinc's concentration was. But again, this value here is going to be so tiny that when you compare it, even doubling it, even when you double this value, when you compare it to what you're starting with, this is like having $1 billion and someone gives you a nickel. It just doesn't matter. The change is so insignificant that we can effectively call this 0.10 molar still. Now, why that's important? If you didn't make that assumption here, then you would have ended up with 0.1 plus 2x, which is the making of a quadratic, and I really want to avoid that. So, in order to make this assumption, though, that this doesn't change, we need to state that assumption. Whoever's grading your test needs to know where this thought is coming from. So you can avoid that confusion simply by saying, since the concentration of the OH initially is so large, the change in that concentration is negligible. If you don't state that assumption here, you aren't allowed to make this assumption mathematically. So I'm going to erase this side because it's irrelevant and I need some room. But let's think about the impact of everything we just said. If you have no clue where to start, just start with an equilibrium expression. KSP equals the concentration of the zinc 2+ times the concentration of the hydroxide squared. Now from the previous problem, we know that the KSP was 3.0 times 10 to the negative 17th. We are still trying to solve for this zinc solubility, so I'm looking for the concentration of this zinc, so I'm still going to call that X. But the difference is now this concentration of this OH isn't based on the dissolution of this guy right here. It's based on the fact that there was already 0.1 molar present. So we're just going to leave that concentration as 0.10 molar. Just don't forget to square it. And now when we solve for X, this is 3.0 times 10 to the negative 17th. As I clean this up, this becomes 0.01 x. So you simply divide both sides by 0.01. And in this case, x, which again is the concentration of the zinc at equilibrium, is equal to 3.0 times 10 to the negative 15th. If we do what we did on the previous problem, we choose to think about this as a separate way. Let me go ahead and put the unit here. That's molar. That means that 3.0 times 10 to the negative 15th moles of zinc 2+ will dissolve in, but it's not water this time. It's not 1 liter of water. It's 1 liter of this 0.1 molar OH solution in a 0.10 molar in a OH solution. So that was a lot, but I really want to just take a moment. I want to take a moment to really compare these here. On the previous example, when we dissolved this in water, we were able to dissolve to a maximum concentration of 1.96 times 10 to the 6th. Now, it's not very much, but when you compare that to what you're able to dissolve in this 0.1 molar NaOH solution, you can only dissolve 3.0 times 10 to the negative 15th molar of it now. That's almost a trillion or a billion times different here, 9 powers of 0 different. The reason this is so much less soluble in this NaOH solution is because of the common ion effect. There was already some OH present in the solution, so that forces the equilibrium to favor the formation of the solid reactant, so far less of it's going to dissolve. That's just a prime example of the common ion effect. So let's look at a couple problems. Here's the first one. What would be the molar solubility of a silver chloride solution if the solution is also 0.001 molar for sodium chloride, and we're given a KSP of AgCl? Well, the first thing I would consider is that I need an equation for this dissolving. We've got our silver chloride. I don't see any of our 4 soluble ions, so I know this is insoluble. It will establish an equilibrium in which there will be silver ions and chloride ions. And again, if you have no idea where to go, just write an equilibrium expression. For this reaction, the KSP is equal to the concentration of the silver plus, times the chloride ions. No powers this time because they're all coefficients of 1. And now let's think about what we know here. KSP, that's provided for us. Silver ions, that's what I'm sort of looking for. We won't dwell too much into it right in this moment, but I'm looking for the molar solubility of silver chloride. And then I've got a chloride ion concentration, but that information is provided as well. If you think about what this means, this sodium chloride has a sodium in it, so it's going to fully dissociate out into sodium ions and chloride ions. So if this is a 0.001 molar sodium chloride, then it's going to be 0.001 molar sodium and 0.001 molar chlorine. Now, which of these is relevant? Well, the only one that's relevant is the one that also appears in our compound that we're trying to dissolve. In that case, that's chlorine. So the concentration of this chlorine is the same as the concentration of the sodium chloride solution. The chlorine's already present, and we're just trying to dissolve it, some silver chloride into it. So we can plug these values in. This KSP is 1.80 times 10 to the negative 10th equals my silver concentration, which I don't know, times my chloride concentration, which is 0.001. This is a super simple algebra equation to solve. We just divide both sides by 0.001. And in this case, X, which is the silver ion concentration, is equal to 1.80 times 10 to the negative 7th molar. Now, we have to be careful and consider that we did not answer this question, but we effectively did nonetheless, because the question asks us what's the molar solubility of silver chloride, not of silver. But if this is the concentration of the silver that dissociated out, then the fact that this is a 1-to-1 ratio tells us that these have the same solubilities. So in other words, even though this is technically the concentration of the silver ions, it's also the molar solubility of AgCl because they share the same coefficient. Let's look at another example. What's the molar solubility of calcium fluoride in a solution of 0.25 molar calcium nitrate? So I can see I'm trying to dissolve calcium fluoride, but the solution in which I'm dissolving it already has some calcium ions in it. So again, I'm thinking common ion effect here, but let's start with an equation. We have calcium fluoride, does not contain one of our 4 soluble ions, so I know it's insoluble. It'll reach equilibrium, in which it'll produce some calcium 2 pluses and 2 fluoride ions. That's a minus. There we go. Again, write yourself an equilibrium expression for this. KSP equals the concentration of the calcium 2 plus times the fluoride ion concentration squared. Now, they provided us a KSP here. And they also told us that the concentration of this calcium fluoride is 0.025 molar. Well, since there's 1 calcium for every calcium nitrate, this also tells me that the concentration of this calcium is equal to 0.25 molar. So when I go to plug in some information here, this KSP is 3.45 times 10 to the negative 11th. The concentration of the calcium is 0.25. Now, however, I forgot to do this in the previous problem. Technically, this concentration is going to change because still some of this will dissolve. But we need to state the assumption, which I neglected to do in the previous problem, but we need to state this assumption that since the calcium 2 plus ion concentration is so large, the change in that concentration is negligible. That's letting us simply plug in this 0.25 for our number here. Otherwise, we technically would have to worry about the fact that technically a tiny bit more of it does dissolve. But that brings us to our fluorine concentration. Well, we don't know that. You can call it X, you can call it 2X, and I understand you might call it 2X because there's 2 here. I would just call it X to simplify the algebra. And don't forget to square that. So now we will have to divide both sides by the 0.25 to get the x squared by itself, 0.25. And then, of course, to get rid of the square, we'll square root that all. So I'm looking at the square root of 3.45 times 10 to the negative 11th divided by 0.25. Make sure when you plug it into your calculator, you plug in this part first and then take the square root of it. But you're going to end up with an x value of 1.17 times 10 to the negative 5th. But remember what you just solved for. We set X to equal the fluoride ion concentration. So this is the molarity of the fluoride ions. But that's not what this question asked. This question asked what's the molar solubility of calcium fluoride. Well, for every 2 fluorines present, 1 of these calcium fluorides had to have dissolved. So we're going to use those mole ratios here. For every 2 molar fluoride ions, I only have 1 molar calcium fluoride dissolving. So actually I need to divide this number by 2, and that will find me a value of 5.87, sorry, I'm out of room, times 10 to the negative 6th molar CaF2. That is the maximum amount of CaF2 that will dissolve in 1 liter of water.